dissolves like, this is what they're talking about. Like if you have two polar things, they will dissolve in each other, and two non-polar things, they will dissolve in each other. But if you take one from each, they're going to form layers, basically. Okay, so ethanol. Ethanol is a type of alcohol. Let's see, ethanol, methanol. Ethanol has two carbons, okay, and where these dashes are, those are hydrogens. That's ethanol. So this actually is what makes it polar. So it falls over here. So your alcohols generally have this, what we call hydroxyl group. Your alcohols are going to have a bit of polarity to them anyway. This is then showing you, it looks like a busy slide, but you can kind of see this is what I drew over there. Here's the two carbons for your ethanol, the hydrogens around those carbons, and then this is that hydroxyl group that I drew. And of course you can kind of see that 3 water molecules. And the red dot, 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 that actually is the intermolecular bond. This is actually showing how it's mixing. So that's a happy sort of situation. Those are two polar molecules, specifically that they are actually hydrogen bonding. Because remember, if you have a hydrogen to an oxygen, a hydrogen to a nitrogen, or a hydrogen to a fluorine, the NOF, hydrogen to any of these, you can actually hydrogen bond. So that's the deal there. Like dissolves like. Well, what about unlike? Well, they would dissolve each other too. Okay, so oil is nonpolar. Another nonpolar substance is carbon tetrachloride, CCl4, nonpolar. Okay, carcinogen, I believe. But it's great at, if you have oil, I'll just put oils up here, oils, etc. Okay, then you want it to dissolve in something, that's a possibility. But a polar compound will not dissolve in a nonpolar solvent. So if you're into the whole Italian salad dressing, okay, so now there's different, but common type of Italian salad dressing has the water, the oil, and the spices, you know. So the water and the oil do not mix. Water and oil do not mix because we have polar and non-polar. So I have a little, what's that?
So, and then also then the non-polar compound will not dissolve in polar.
Correct. Okay. Yes. Yep. A non-polar will not dissolve in a polar. Non-polar solute will not dissolve in a polar solvent. Yep. So here's a short little video. Let's see what you think. Number 8, and then I brought my thing. So you guys have a test that opens up tomorrow, actually, for Unit 3, which is chapters 5 and 8. And the test will be open through the next Monday. Okay? Okay. So as we're talking about water, we definitely need to hit on the subject of acids and bases. And I feel like we hit this in lab, but we're going to hit it again, kind of in a different way. So an acid in general is one that provides H pluses. So H plus is the thing there. So what do we call the H plus? Well, we call it a few different things. We can call it the hydrogen ion, but we can also call it just simply a proton. So the word there is proton. And the way that works is this. Hydrogen atom. Hydrogen is atomic number 1. So if I was looking at a hydrogen atom, it would have 1 proton because it's atomic number 1. Its most common form, and this is the nucleus, its most common form is actually a mass number of 1, which is protons plus neutrons. So it actually has no neutrons. And if I'm looking at a plus 1, an H plus, then basically that 1 electron, this is the neutral hydrogen atom, for an H plus, that 1 electron has gone away. So for an H plus, this is what it looks like. It basically has 1 proton in the nucleus, it lost its 1 electron, okay, and it has no neutrons. So H plus is also called just a proton, which is kind of fun. So again, with the chemical equations, we could say HCl, HCl breaks apart, AQ means in water, to form H plus and Cl minus. Not good, bad, or otherwise. A lot of times I'll get, I guess it's sloppy. I won't put these AQ here. So I think in your notes, if you just want to put H plus and Cl minus, you could. Or you could include the AQs. So we're just showing it. This is called dissociation or ionization, dissolved. The word is completely down there. HCl dissociates completely into H plus and Cl minus. So there are different types of acids, and HCl is an example of a strong acid. There are 7 strong acids. HCl is one of them. And it's strong because it breaks apart or dissociates entirely. So another thing, or the H plus, and I read this in your textbook just recently, the H plus is very reactive. So H plus catches a ride with an H2O molecule. Okay? When it catches a ride with an H2O molecule, it forms what we call the hydronium ion. Hydronium is H3O plus. So I'm kind of surprised I don't have a separate little chemical reaction for that. But what I'm describing is this H plus, it's in water. It's going to catch a ride with a neutral H2O molecule and form H3O with a +1 charge. That's called hydronium. Sometimes I call it the hydronium cation or hydronium ion. Okay. So if we were to kind of take this approach, and again to look at our strong acid breaking apart, now on the product side, we would show that what it forms is H3O plus, that's hydronium, plus your Cl minus, the chloride ion. Again, the AQs get kind of sloppy. So that's probably more the reality. And there is your hydronium cation. It runs around with a +1 charge. There's your neutral water molecule in there somewhere. There's your water molecule and an H bumped up. So let's see how we do with these. We're supposed to go ahead and, let's see, for each of the following, write a balanced chemical equation that shows the release of a proton when dissolved in water. And then also go ahead and show the formation of hydronium ions. So let's do like we do sometimes going around. Help me out, Autumn. If I put HI, so that's iodine, right? It's going to break apart to form what? H3O plus, positive,
And then iodine.
And its I is going to be what, a -1. Does that seem right? Yep. Because it's this is an ionic compound, and you have an H plus and an I -1. And also, your I is a 7A element, and you know that it forms a -1 charge. Very good. Now, the one thing that's missing, I'm going to go over here on the reactant side, I'm going to put H2O. And that is just my rider. That was the water molecule that my H plus caught a ride on.
You wouldn't just put that like over there? Or?
Well, to show its balance, I think the example that I did on the previous slide, I showed it as a reactant instead of over the arrow. Because otherwise it kind of, we reserve this way it's balanced. Does that make, we talk about balancing equations. Actually this way we have what, 3 hydrogens on both sides, 1 oxygen, and 1 iodine. So probably the right way to do it. Okay, so Natalie, help me out with the next one. What do you think? HNO3, which is nitric acid. Think of it as that H plus is going to get kicked off. So what would it look like on the other side? You can either just kick the H off, or you can have the H combined with a water molecule, either way. And to give you a hint, this is one of those, the NO3 is going to stick together. That's nitrate. Yep.
Then is it H3O plus NO3?
Very good. NO3. And what charge do you think that might have? If over here, this is a +1, so what was this must be? If the whole thing needs to be neutral. This is +1.
-1.
Right, exactly. Yep, that's a -1. And I think I'm going to go ahead and on the reactant side, I'm going to put it my writer H2O molecule. So H2O plus HNO3 goes to form H3O plus NO3 minus. Very good. Okay, Billy, so for the next one, I'm going to go ahead and this, I don't know if you remember, but SO4 is sulfate, so it's going to stick together. So what do you think?
Is it H4O?
So it's going to go to form, no, it is an H4O. We could think of this a couple ways, and actually I think I have a slide coming up explaining this. When you have two hydrogens that could kick off, the first one's actually the only one we're going to worry about, and the other one's going to stick with it. So I kind of told you wrong. After it goes, you're going to get something called the hydrogen sulfate ion. I don't know if that makes sense, but only one of them's going to go. So H3O, yep, plus. Yep, HSO4. And it's a -1. Yep, -1 charge. And then I'm going to go ahead and put my writer water molecule over there on the reactant side. Very good. Okay. So now, acids versus bases, and I think in lecture we talked a little bit about that. Bases are kind of like the little bit the opposite of acids. One of the things I like to think, it's funny because I'm getting this class and my General Chemistry 2 class mixed up because we just talked about this. If you take a water molecule and if you break it apart, you're going to get an H plus and an OH minus. Okay? Now, I think of it like that because it works. Actually, your H pluses are going to be acids or acidic solutions. Your OH minuses, which is we call hydroxide, the hydroxide ion, that's actually going to be associated with your bases. Okay. So bases are something then, so the word is bases up here. The flip side of the story in chemical is opposite acids or bases. The word is hydroxide there. So a base is something that gives you OH minuses, one way or the other. That's what a base is. And you can't have both. You can't have something that's both acidic and basic. Okay. Make sure I got me. So bases generally taste bitter. Bases generally feel slippery. And bases, if you're, remember, and I think with y'all, it was Miss Natalie who went and, for last Tuesday's lab, went out and got the pHs of your sample. But there's this paper different types of paper, and in terms of litmus paper, bases will turn litmus paper blue. Acids will turn litmus paper red. Okay, so an example, okay, so we'll go around. What does, Autumn, what does K stand for? What element is K? It is potassium, very good, potassium. So this is potassium hydroxide. Natalie, when it says group 1 or 2, what are we talking about? Hint is on the periodic table.
The columns.
The columns, perfect. So 1 and 2, yep, potassium's there, and then this is group 2. So these guys, they do pretty good being cations and combining with hydroxides to give you a source for base, to get a base, okay? So, I think I'll ask in the form of question. This one then breaks apart, your OH minus stays together, and it gives you this. Again, the AQs are optional. But KOH breaks apart to give you K plus and OH minus. And this is kind of like what Autumn was saying, over the reaction arrow, we're just showing that it's in the presence of water. Very good. So, Billy, what would be different? And this should be a subscript instead of a big 2, it should be a little 2. Now, calcium hydroxide, Billy, is a little bit different. What would, well, we'll do this in pieces. Calcium, if you look at the periodic table, what charge is it going to form? What plus? Plus 2, very good. And then, so Autumn, the other thing that's different, so Ca plus 2, how many OHs are you going to get? This is supposed to be subscript 2. We're going to get 2, exactly. So then on the product side, that's why it says Ca plus 2 and 2 OH minus. You get $2 for your bang. Very good. Now, NH3, you're like, now ammonia, the formula for ammonia is NH3. You're like, how in the heck do I get OH minuses out of NH3? I'm going to show you how that works. But ammonia isn't a strong base, but it's a base. It gives you a base as it reacts with water. So actually, it's not a strong base, it's what we call a weak base. Weak base. And in my my other classes, a lot of times I'll go, this makes sense, right? WB for weak base. And this guy up here, potassium hydroxide, calcium hydroxide, that's an SB for strong base. So this is how that works. I mentioned it interacts with water. So here we have NH3 and an H2O. Now, one of the things that's different right away, and I wish it was bigger. That actually has an arrow going this way and an arrow going this way. It has what we call a double arrow. And that is a big, hairy deal. So whenever in chemistry you see a double arrow, it means it goes from left to right, the top arrow, and it also goes from right back to left again. Well, let's see how we get the hydroxide. Here's how we get the hydroxide. On the product side, it's NH4 plus OH minus. NH4 plus OH minus, or minus 1. That's your hydroxide. That makes it a base. And do you see where it actually, I use the word abscond. What happened was NH3 took or absconded a hydrogen from a water molecule and made NH4 plus. Not just any hydrogen, but it took an H plus from a water molecule, left behind a hydroxide. So that's why ammonia is weakly basic. Okay. So equilibrium is the word there, equilibrium. If you see a two-way arrow, that is a reaction that is in equilibrium. It goes from left to right, and it goes from right back to left again. The other thing, or another thing pointed out here, the word is conjugate. If you can find two things, we say that differ by an H plus, they are related. We call them a conjugate acid-base pair. So the conjugate acid-base pairs, conjugate acid-base. The things that differ by a proton here would be your NH4 plus and your NH3. Okay? Then they're related by an H plus. They're a conjugate acid-base pair. And doesn't that look like it's just itching to give off an H plus? Your NH4 plus, give off an H plus. That's what, so actually it's a weak acid. And NH3, I said how it gets to be a weak base is, like I showed you up here, it has to react with water to be a hydroxide. Differ by a proton. Differ by an H plus. And you see how OH minus and H2O differ by an A plus? They are another example of a conjugate acid-base pair. Those a few slides ago, when we did your terms, you guys did conjugate acid-base pairs there too. Okay. So if you think of it this way, we're going to see some common household, some common household chemicals and things that we eat. And we're going to see there's some acids out there and some bases out there. It's quite possible if you take something that's acidic, like tomato juice, and react with something that's basic, like ammonia, you could actually get a neutral solution out of it. Okay, acids and bases come together to, depending upon their strength, make something that's neither acidic or basic. Okay, it's what we call neutral. And like I said, depends on their strength, depends on what else there is in the solution that might be working towards or against it. Okay, so when neutralization happens, the H pluses combine with the OH minuses to form, what do you think they'll form? What's an H plus? What's an OH minus? H2O to form water. Yep, exactly. They find each other.
But just water?
If it's just H plus and OH minus, that part of the neutralization is going to make water. Now there are other parts that's going to make what's called a salt. Yes. It's also the other thing, and I think this is what you might have been talking about. The other thing that's formed aside from water is salts. Now, here's where I have to say, and when we started this class, you guys told me salt is NaCl, table salt. But I'm going to tell you that anytime you take a cation like sodium and an anion like chloride, you put them together, make an ionic compound, that is a salt in chemistry.
So it has to be.
What's that?
In order for it to be a salt, it has to be ionic.
Yep, to be a salt, it's an ionic compound. Exactly. Yep, you got it.
So you could have an NaCl that's not.
Nope. NaCl, the fact that you have something that's a cation, sodium, and an anion chloride, that will always be an ionic compound. Yeah. And that has to do with electronegativities. All right, so let's take a look at some neutralizations, or a neutralization. Okay, so who did we leave off with? Hey, Natalie. Okay, so Natalie, in this HBr and BaOH, that should be a subscript too, sorry about that. What's the acid? Is it HBr or BaOH? Two. Which one's the acid? Which one's going to donate an H?
Oh no, the HBr.
Yep, the HBr. Yep. So that's your acid. Yep. And this is your base. And I told you that actually this H plus is going to go with these OHs to make water. They just are. So that leaves behind the BA and the BR. Okay, so Billy, help me out. What the BR, what sort of ion will that form? The BR. On the periodic table, so it's right over here. So what sort of ion will it form? Negative. Negative 1, perfect. So BR is a negative 1. I'm just kind of drawing this in the margins, kind of. All right. So help me out, Autumn. BA, what sort of ion will it form? Yes, a 2 plus, yep. So BA 2 plus. Okay, Natalie. So if I want to make a new compound BA with BA and BR, and I usually say kind of crisscross, crisscross, how many of each do I need to make a neutral formula? So how many BAs do I need, and how many BRs do I need? Yep. BA-BR2. Perfect. Thank you. BA-BR2. I know it's kind of messy up there, but that is the salt. So when we work these, or when I show the products here, you're going to see water and that BA-BR2. So here on the product side, now I have BA-BR2 plus 2 H2Os. Do you see why I get 2 H2Os? Because I had 2 H's from my 2 BRs, and I had 2 OH's from my BA-OH quantity 2, combining to make my water. So it's balanced. Any questions about that? Well, one of the things about it is BA-BR2-AQ is going to break apart. Okay. Excuse me. So let's see. We're up to you. No? Yeah, we're up back to you, Billy. So say BA-BR2 breaks apart in water. We call that ionizing. How many BAs do you have? 1. Perfect. And then how many BR minus 1s do you have? Perfect. Yep, you got it. So the next thing I have is basically just kind of showing you that ionization. So what's different here is I'm showing, well, I guess I'm showing 2 things. Oh, it's a mess. I'm basically breaking it apart. Should we read this out? Or you don't have the products? Yeah. Okay. So the first part, I broke up the 2 HBr, and I gave 2H plus 2 BRs. And I broke up the BaOH2, I got Ba plus 2H minuses. And then on the product side, and I ran out of room, so that's why it's kind of folded around. Just like you were saying, I get the 1 Ba2 plus 2 Br minus plus 2 H2Os. Now, the only reason I would want to do this ionic one is so I can whittle it down to what's called the net equation. Here's the deal. If between my 2 hands is a reaction arrow, and if I see the same thing over here and the same thing over here, I can combine those terms. It's like math with an equal sign, but it's an arrow. It's like math. Ugh. So here's the deal. If I have the same number on both sides of the arrow, the equal sign, they go away. And that's exactly what we've got. So for instance, do you see where with this ionic equation, I've got 2 Br minuses on the reactant side, and I've got 2 Br minuses on the product side. They both go away. I've got a similar thing with my Ba2+. I've got 1 Ba2+ on both sides. Now, if I had an equal amount, I could still at least combine terms and kind of subtract them from both sides. Okay? So then this distills down into, from the ionic, we can come up with what we call the net ionic. Cancel out things that are common on both sides. So to me, all we got left is the 2H plus 2OH minus going to form, or on the product side, 2H2Os.
So you have written like that, you have to like make a note that this is your ionic formula?
Yeah, yep, you make a note, that'd be
referring a lot otherwise.
Yeah, so maybe this is your point. Any neutralization kind of distills down to this. Any neutralization reaction, a neutralization is just the acid and the base. When you get to the crux of the matter, what the chemistry going on is simply your H pluses combining with your OH minuses to make water. So this is what we say balanced for, if you drew the brick the brick wall here, you counted hydrogens and oxygens. Hydrogens and oxygens, you have the same number. But now the coefficient, which is what the 2 is, those 2's kind of can drive us nuts. We can actually multiply through by 1/2 and scale it down to simply this. So scale down, or however you want to think of it. Basically took the whole recipe and divided by 2 and multiplied by 1/2. Instead of 2 H's, we get just 1 H. Instead of 2 OH's minuses, we get 1 OH minus. Instead of 2 H2O's, we get 1 H2O. We can do that with any balanced equation. So yeah, that's actually, anytime you have a neutralization reaction, that's kind of at the crux of what's going on. Okay, I think we might come back to this one, but I don't want to take the time right now. We'll either come back to it or I'll make a sheet on it. Because I do want to get to this idea. So pH says how acidic or how basic your solution is. You guys used a pH meter, okay? So like I said in lab, your meter has that sensitive little probe thing, and that little probe thing is detecting your H plus ion concentration. It's pretty cool. Now pH is the P in pH is actually just a mathematical function. It's a P function. And anytime you apply a P function, you basically take the negative log of that quantity. So pH is the negative log of the hydrogen ion. So let's see, I brought my calculator. I have your calculator. I have you guys play around with this. Billy, you have a calculator? These little itty bitty ones. LG. That's how to use it. So that's pH. Okay. So go ahead and tap this into your calculator. So if we have the hydrogen ion concentration, and if you don't want to mess with scientific notation, let's see, 1 times 10 to the minus third is 0.001. It's the same thing. So what you need to do is go ahead and sometimes the negative, don't worry about the negative if you don't want to. If you want to do the negative, you hit your plus minus key, You hit your log key, put in 0.001, and then I think you push enter. Okay. And if you didn't hit your negative key, it should say negative 3.0 or negative 3. If you did hit your negative key, it should say 3. Did you get it?
Am I putting that whole thing or just?
So you're just going to do this one, right? To put log of, and if you want to put 0.001, that should work. Log of 0.001. Oh. So if you hit the log key, you're right. Put 0.001. Is yours work, Billy?
I don't think it has a long key.
Yeah, it's kind of the middle.
Oh.
I got one up here. Did yours work?
Yeah.
Oh, it's like keeping error. Oh, maybe you were right. Try 0.001 and do log. Okay, that happened. Okay. So for this calculator, you have to put in the number and then hit your log key. I give you negative 3. Oh, did it work for you then?
Yeah.
Are you using your other calculator?
Mm-hmm.
Okay. The problem, or the reality of this scale is each pH unit change is a factor of times 10. So it's not linear, it's 10, factor of 10. So, did it work? Yay! So the words are power of 10. Cool. Okay, so if we say a solution, we would compare pH of 2 and 3, you're looking at the pH 2 is more acidic, right? So it has 10 times. Now that's one of the things that maybe you don't know yet, and we're going to hit this again when we meet on Wednesday. But I had mentioned this before, and you're going to see this at the end of this notes. The neutral pH is 7. And as you get lower in pH, that's more acidic. So you're increasing acidic. And if you get higher than 7, that's becoming more basic, increasing basicness. Okay. So 2 and 3, okay, so here's 2 and here's 3 on the pH scale. This is more acidic. Specifically, it's 10 times more acidic. It's a big hairy deal. Oof. So let's just do the first one. I'll do it on my janky calculator. You guys do it on yours. Let's see if we get the same number. Now this one's a little complicated because we're going to have to figure out scientific notation. Either that or go with 4 preceding 0.4444. Sorry, 0.000045 will also work. And I'll go with 2 decimals. Did somebody else get this? I got 4.3. Okay. Yeah, but the log function is the negative log. So So if it will come out negative, and then you multiply it by -1, so it's positive. I want to do the last one too. 6. And I got 7.0.
How did you get these answers?
How'd you get what?
How did you get those answers? Am I just putting that in as it is, or
Do negative log and then just plug in the which side.
7.0?
So for yours, I think it's kind of like this one. So
So you're put it after?
yeah. Yep, there you go. You get it? Sweet. Okay. Somebody who did B and C, what'd you get?
2.67 and 8.1.
Thank you. Okay. Very good. Well, that's all I have today. We'll pick up here, and by golly, we got to knock out chapter 8. Getting on my nerves.
Okay, unintelligent.
What's that?
If I wasn't here today, I'd be really confused tomorrow.
Yeah. Oh, glad you're here. So remember to check your emails just in case.